So good morning to all. Today we are here to discuss about harmonic oscillator case by using microcanonical ensemble representation. Okay. So in the last class we have discussed about classical ideal gas, and we are identified the thickness of hypershell and the volume of the hypershell, and also finally we identified the fundamental volume of a single microstate. Okay, that is omega 0, which is equal to h raised to 3n. Then if you represent h raised to 3n in fashion of degree of freedom in terms of f, then omega 0 equal to h raised to f. Okay, so that was the intake from the last class, and now we are considering here the case of an harmonic oscillator. Okay, and we know that in a harmonic oscillator we'll be treating this as a one-dimensional problem. Okay, so we are treating a one-dimensional problem here. Okay, and we know that the Hamiltonian corresponding to an harmonic oscillator, so it is a sum of the potential energy plus the kinetic energy, so that is half qp. Okay, hqp is equal to, we can represent as hqp equal to half kq square plus p square by 2m. Okay, so and also we know that the representation of the position when you consider for a harmonic oscillator, for an harmonic oscillator case, that is equal to a cos omega t plus phi. So this is the position representation or the solution of the equation. We will be having q equal to a cos omega t plus phi. Okay, where we know q is representing the position of the particle, p is the momentum of the particle. So here we are having a one-dimensional particle, and also from this representation we'll have a means a is the amplitude of the wave, and also omega is representing the angular frequency. Okay, it is, you're already knowing these things, and phi is representing the phase. Okay, phase change. And now we know that p is equal to the momenta, p is equal to what? It is basically mv. So here you can represent that is mq dot. Okay, mq dot will be there. Okay, that means you have to take the dq by dt. So that is mq dot means I can represent this will be equal to ma. Okay, q is a cos omega t plus phi. So that is ma minus omega sin omega t plus phi will be there. Okay, so once I get the momenta, so I can represent that in terms of, that is minus m omega a sin omega t plus phi is the reducible form of momenta that is obtained here. And we know that when you consider a one-dimensional harmonic oscillator where omega is equal to what? Omega is equal to root k by m, where k is the spring constant, right? Okay, so omega equal to root k by m. And now what I do is that the above harmonic oscillator representation, that is where the Hamiltonian basically representing the energy. Okay, so this is a Hamiltonian actually representing the energy, and this equation becomes, so I can substitute corresponding to q, and I can also substitute corresponding to p from the above equation. So this becomes what? This will be equal to, in terms of energy, because Hamiltonian is a total energy representation, right? So E equal to half k square cos square omega t plus phi. Okay, and plus we have to also represent p equal to, p can substitute as minus omega a sin omega t plus phi. That means I will be getting p square equal to 1 by 2m into p square becomes, p square is m square omega square a square sin square omega t plus phi. Okay, so this is how energy term will be after substituting P and Q. And now, and this representation we can have a reducible form, because when you take half k, k means what? From the above representation we already have omega equal to root k by m, right? So this I can represent as k square if you take omega square. Okay, so if you take omega square, this will be m omega square la, m omega square will be there. K equal to m omega square you can obtain from that. Okay, from that representation we could identify that when you take this, in this part you cancel this one, that is you will be getting k, I can substitute as m omega square, a square cos square omega t plus phi plus 1 by 2m into m square, so that square and this m will get cancelled, that is 1 by 2 into m omega square a square sine square omega t plus phi will be there. Okay, now I can take 1 by 2 m omega square a square outside, that is cos square omega t plus phi plus sine square omega t plus phi. Okay, so this is equal to E equal to what? Energy E equal to, so I will be having the final version is 1 by 2 m omega square a square will be the energy representation corresponding to a one-dimensional harmonic oscillator. Okay, so this is what I got from this one. And now let me come to another stage. So here you just note down the energy is half m omega square a square. Now we already know that Q equal to what? Q equal to a cos omega t plus phi, and we know that P equal to what? P equal to minus m omega a sine omega t plus phi. Okay, now let me write this one in this fashion, that is q by a equal to what? Cos omega t plus phi will be there, and similarly minus p by m omega a is equal to sine omega t plus phi. Okay, so I can write like this, right? Okay, from now if I do, okay, now if I square this q square by a square, that is if I can write q square by a square plus p square by m square omega square a square, that equal to 1, because cos omega t plus phi, cos square omega t plus phi plus sine omega t plus phi will come. So that this equation after squaring, if you add together, you will be getting the corresponding representation which is equal to 1. Okay, now we know that this is a representation of an ellipse, right? Okay, so this is in fashion, that is q square a square plus p square m square omega square a square, means it is like x square by x square plus y square by b square, which is equal to 1. So this is the equation of ellipse. So this is equation of ellipse that is we are getting here. Okay, so in this case let me make a small more change as well. So as we know, energy is equal to what? Energy is equal to half m omega square a square. So and from that I can write a square equal to 2e by m omega square. Correct? So equal to half m omega square a square. From that a square equal to 2e by m omega square. So now I can substitute that into the equation. So that is q square by a square I can substitute as 2e by m omega square plus p square divided by m square omega square into 2e by m omega square. Okay, so this is how I will be getting the value, and now which is equal to 1 as well. Okay, so this is equal to 1. Now from this one we can represent this equation becomes q square by 2e by m omega square plus the in this one omega square and omega square get cancelled, and m square get cancelled, that is p square divided by 2em is equal to 1. So this is how I get. And now if I just compare this with the equation of ellipse x square plus y square by b square is equal to 1, which is the equation of ellipse, while comparing I will be getting the value corresponding to, so where this is this equation actually representing an ellipse. Okay, so this is tracing an ellipse here. So where a square equal to what? A square equal to 2e by m omega square, and b square equal to 2em, and from that I can have a equal to what? A equal to root 2e by m omega, and b equal to root 2em I will be getting. Okay, where a and b is what? A is the major and minor axis of an ellipse. Okay, so these are the major and minor axis of an ellipse. And now if I say the axis value is proportional to, in the both case you can understand that the axis values, whenever you consider a or b, the major or minor axis, okay, so the axis is proportional to what? Root e. Okay, so in both cases you can see that this major axis a or minor axis b, so which is actually proportional to root e. So that is what we are getting. Now if I trace this one, so what I will be having, so I will having an elliptical shell here. Okay, so assume that this is an ellipse. Okay, so I will have an elliptical shell. Okay, and here this is a phase space diagram. We know that phase space diagram will plot with respect to momentum and the position coordinate, and we can say the inner one is actually representing e minus delta by 2, and the outer one is e plus delta by 2, like if you apply microcanonical ensemble case. Okay, so from the microcanonical ensemble, what do we say is that the energy will be the Hamiltonian energy, the total energy of the system will be between e plus delta by 2 and e minus delta by 2. That means it will be in this region. Okay, so this interval only you can see the total energy and the number of microstates corresponding to this. Okay, and this part of the value will be actually the delta. So this difference will be delta in this case. Okay, okay, so with that discussion let me go forward. So that is when you consider the area of ellipse here. Okay, area of the ellipse is equal to, we know that equation is pi ab. So what is a? A is root 2 e by m omega square into 2 root e m. Okay, sorry. Okay, root t m, and from that we'll get if you multiply this one, you will be having you will be getting 2 pi e divided by omega square, because m and m get cancelled, then you multiply root 2 e square will be there, that is 2 pi e by omega square. Okay, so this is the area of the area of the ellipse. Okay, sorry, so it is the area of the ellipse. Okay, so that is what we got. And now if we said that axis is proportional to, here you can see that axis is proportional to root e, and in this case when you say the area of an ellipse, okay, area of an ellipse, okay, it is proportional to e, not root e, it will be proportional to e. From the equation itself we can say, because it is area is 2 pi e by omega square, that is area is proportional to e. Okay, now you understood that. Now let me come to this above case, because when you apply microcanonical ensemble case, okay, by applying or by using a microcanonical ensemble case, okay, ensemble, in that situation we say that the energy lies between E minus delta by 2 less than or equal to HQP, okay, less than or equal to E plus delta by 2 region. Okay, and in this region we will have the corresponding case. And now also we say that when you consider an hypershell of ellipse, so we'll be taking the area into consider. Instead of taking the volume, we'll approximate that into the area. So the total volume means we are taking the area of the ellipse, that is equal to omega. Omega is the total volume of that particular energy interval. Okay, like the same that we have done for the earlier case of uh, in the case of a classical ideal gas. Okay, and here we know that when you consider this case, we'll have a 3 n-dimensional position coordinate and 3 n-dimensional momentum coordinate. Okay, that is total, in total we'll have 6 n-dimensional case. Okay, so when you picturizing that, is it is a bit difficult to consider that, and since we are only dealing with one dimensional particle here, and we'll have one q particle, that is one position associated one, and we'll have only one momentum coordinate also, because we are treating only one dimensional particle here. Okay, and we are taking only one position coordinate and one momentum coordinate. That means we are representing a 2D representation. 2D means we'll have momentum on the x-axis and momentum on the y-axis and q on the x-axis. So totally it is 2-dimensional. That means we need to consider only what? We need to consider only the area, because we are considering a 2D state. Okay, so that's why the volume of the ellipse we are approximating to an area. So that is equal to omega, where omega is the total volume that is approximating to area, since it's a 2-dimensional case. Okay, so it's not a 3-dimensional case, 2-dimensional case. So we are having an area corresponding to that, and in that representation we'll have omega equal to, we simply need to take dq and dp. In last classical ideal gas we taken dq raised to 3n and dp raised to 3n. Since it's 2-dimensional, we can just represent dq and dp corresponding to that. Now what I do here is that, let me say that the corresponding value of so when you consider the area, we basically taking the area between these two energy levels, that is E plus delta by 2, E minus delta by 2. So we are interested on the region, okay, we are specifically interested in this region, so we are specifically interested on this particular energy interval region. Okay, so in order to take the energy of this particular area, or the area of so I want to find the area of this specific location, this specific area where I shaded with the blue and red marks. Okay, so I need to get the area of this one. In order to get the area of that specific in terms of energy, so I want to basically take, so I need to take basically the 2 pi. Here already we are having equation corresponding to what we already identified. the area is equal to what? Area equal to 2 pi e. Okay, so we got equation that is 2 pi e by omega square. So in that equation, so let me just introduce 2 pi e plus delta by 2 divided by omega square minus 2 pi e minus delta by 2 by omega square. So that I will be getting the area, that particular energy interval or that particular area I can obtain by taking the difference of these two energy levels. Okay, so from that representation I will be getting, when you do that, omega equal to the volume or area corresponding to this case. Okay, omega equal to, I will be getting 2 pi, and this omega is angular frequency. You identify that 2 pi by omega square delta will be the resultant value I will be getting, and this omega is the volume. Okay, and this one is angular frequency. Okay, so do not confuse that. Okay, so this is actually coming from the solution of a harmonic problem, that is q equal to a cos omega t plus phi. So this is the angular frequency, and this is actually the volume, the volume of the particular energy interval. Okay, so what I obtained is that it is equal to 2 pi omega square delta. Okay, so delta is the energy difference or the energy interval between E plus delta by 2 and E minus delta by 2. Okay, so this is what I am getting. Omega is equal to 2 pi omega square, 2 pi omega square delta. Okay, now when I represent this value, I can say that when I consider an ellipse like this, okay, so which have another ellipse here and which have another ellipse over here. Okay, so when you say that it is energy is condensed in this stage, we know that En equal to what? N plus half h cross omega is the condensed energy state, and where E0 equal to that N equal to 0, that is half h cross omega will be there, and E1 equal to what? E1 equal to 3 by 2 h cross omega, and E2 equal to 5 by 2 h cross omega, like that. Okay, so when I do represent that in the figure, this is the area corresponding to half h cross omega, and this is 3 by 2 h cross omega, and this is 5 by 2 h cross omega. Okay, so these are the different energy level. Again, this is P with respect to Q, and from that I can identify the different eigenstate corresponding to the harmonic problem. Now if I say the difference between, in this case, difference between two eigenstate, because eigenstate representing the two different energy levels, right? Okay, from that I can say that 3 by 2 h cross omega, that is, I am just taking E1 minus E0, that is equal to 3 by 2 h cross omega, half h cross omega, that is I will be getting h cross omega corresponding to that. Okay, so I will be getting h cross omega, and similarly you can also do E2 minus E1. So actually we are taking the difference between two nearest, okay, two nearest eigenstate, okay, two nearest eigenstate. So E2 minus E1 means, that is 5 2 by h cross omega minus 3 2 by h cross omega. Again you are gonna get as h cross omega. So that is the difference here. Okay, when the energy is condensed, we will represent that is n plus half h cross omega, that is already we know. Okay, and the energy difference what we obtained here is that h cross omega. Now if the number of eigenstate within the allowed region, because allowed region is the region where we are in the particular energy interval delta, that is it is a region between E plus delta by 2 and E minus delta by 2. Okay, so in the allowed energy region or energy interval, so the number of eigenstate, okay, so let me just rewrite it. So number of eigenstate within allowed energy interval delta is, okay, in that case the number of microstate will be, that is delta by h cross omega. So it is the number of microstate. So it is the number of microstate within the interval delta. So that is delta by h cross omega. From that we can, that number of microstate I can represent as, for example, t equal to the number of microstate, that is t by delta h cross omega. And now, sorry, not t, so it's gamma. Sorry for saying it's t, it's actually gamma. So what is a gamma? We know that gamma is actually representing, gamma is the number of microstate in a particular interval. So gamma equal to delta by h cross omega. Okay, so this is the number of microstate in the particular energy interval. Okay, so this is how we are getting here. Now, so we got the representation of gamma, that is number of microstate. Now we need to identify the fundamental volume. Okay, so fundamental volume associated with that, that is omega 0, or fundamental volume or the area of a phase space for one eigenstate. Okay, that is that we call as the fundamental volume. Okay, so the fundamental volume or the area of a phase space for one eigenstate, that is equal to omega 0 equal to we know the equation, we have identified the relation in the case of microcanonical ensemble, that is gamma equal to omega by omega 0. Okay, from that representation, okay, the fundamental volume is equal, means endane fundamental volume ennu parnal, it is a volume of a single microstate, or rather we can say that it is the area of a phase space for one eigenstate. Okay, so gamma equal to omega by omega 0 relation we already identified in the case of microcanonical ensemble. From that, omega 0 equal to what? Omega by gamma, and already we identified omega equal to what? It is 2 pi omega square delta, and gamma equal to what? It is delta by h cross omega. Okay, now if I substitute this into the equation, okay, one second, let me just take the equation. We'll have h cross omega square, right? Okay, delta omega square. So that is, if I substitute 2 pi delta by omega square divided by delta by h cross omega. Okay, so that I'll be getting the value this let me just check it somewhere I have done some mistake or not, because it's okay. Sorry. Okay. There was a small correction, so let me, because when you come back to here, because here if you do that, multiply this here, then actually there will be only root omega square is under the root, right? So there will be no square here. 2 pi e by omega will be there. Okay, sorry to the for that, because here you have to take root 2 e by m omega square. So that is root 2 omega square means you will be having only omega. Okay, so if that is the case, let me just say that this I will be keeping as a bigger one, so that you won't confuse. Okay, and now if I come to here, so here also there will be correction, that is simply the square won't be there, and here also there will be no square. Okay, and here also there will be no square. Okay, so sorry for that. 2 pi delta by omega. Okay, so do that correction in your case. And now if I come to here, here also this omega is equal to 2 pi delta omega. Okay, so 2 pi delta by omega, that means I will be getting the value, so that is equal to 2 pi h cross, that is omega 0 equal to, okay, omega 0 equal to 2 pi h cross will be I am getting here. So if I say omega equal to 2 pi h cross, we know that h cross means what? H cross is h by 2 pi, right? So that is where h എന്ന് പറയുന്നത് എന്താണ്? Planck's constant ആണ്. Planck's constant ആണ്. Okay, so from that representation, so if I substitute h cross equal to h by 2 pi, I will be getting omega 0 equal to what? Omega 0 equal to h. Okay, so we have identified a case for classical ideal gas. What was that? That is omega 0 equal to h raised to f. Okay, where f is the degree of freedom. Okay, degree of freedom. Okay, now in this case, the we know that the degree of freedom is equal to 1, that is f is equal to 1 for this case. Okay, so that is omega 0 equal to h. Okay, so like classical ideal gas case, here also we identified the total volume omega, then the gamma, that is the number of microstate. So once you identified those two things, you can also identify the fundamental volume by substituting omega, that is the total volume. Here we consider the volume as an area, because we are considering a two-dimensional case for elliptical case. So in order to find that, so the omega we treated as an area here, so area by number of microstate. Okay, so omega 0 also will be representing not a volume, it is basically a phase space area for that particularly one single eigenstate. Okay, so in anyway, so we'll be getting the fundamental volume or fundamental area for this case, so that is equal to omega 0 equal to h. Okay, so when you will be getting omega 0 equal to h, since the degree of freedom in this case will be equal to 1. Okay, so that omega 0 equal to h you will be getting here. And we know that in earlier for classical ideal gas it was h raised to 3n for classical three-dimensional particle. Okay, classical ideal gas case. Okay, so that's all about the discussion of microcanonical ensemble, and there are two examples of microcanonical ensemble. How do we evaluate with respecting the idea of the microcanonical ensemble? We have identified in two cases. One is classical ideal gas situation, and the another one we have discussed about harmonic oscillator case. Okay, so that's all about the discussion of microcanonical ensemble for now. Now we will all move on to the next discussion, that is about canonical ensemble. There we'll identify what is canonical ensemble and their different features, and after that, like as we have done here, we'll also do the harmonic oscillator problem in canonical ensemble case. Okay, so we'll discuss about canonical ensemble and further on the next class. Okay, today I'm just winding up this session here. Thank you for listening.